So this is 2.3 part 2. All right, so we talked about last time, we talked about division, and we talked about remainders and what the remainders tell us. And we emphasized a couple of times that if our remainder is 0, when we do our division, that means that we have found a root of our polynomial. We found a solution to our equation f of x equals 0. We found a factor. We found an x-intercept, all those things that are the same. Well, we want to know today, well, how do we, if we have some random polynomial, how do we pick the thing to divide with? For all the problems that we've done so far, we've been given something, try this, or given that this is a root, do this. Well, if we don't know, how do we narrow it down? Because there are a lot of numbers to choose from. So what if I said that our problem was to solve x to the third plus 6x minus 7 equals 0. So that was our problem, to solve this. Well, without doing stuff that we've been talking about, this would be, I'm not sure we'd know how to do it. It would be a challenging problem. What if we knew that we had that plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6 are possible solutions? So what if we knew that? How would we go about the problem then? We could plug them in and calculate. So with a polynomial with just a few terms, that would work. If it was a longer polynomial, 5, 6, 7 terms, maybe it's something to the 7th power, that might get a little tedious. What else could we do based on what we learned last time? We can do synthetic division, right? Test it with synthetic division. Synthetic division is just multiplication and addition. And see if you get a 0 remainder. And once you get a 0 remainder, then you've also factored this polynomial. You've reduced the power by 1. So then we have a quadratic that we could use the quadratic formula on. So if we know that if we have a list of possible solutions, we can try synthetic division. And we're looking for a 0 remainder. So that's really in chapter 2, that's our goal when we're solving, when we're finding zeros, when we're finding intercepts, etc. Our goal is synthetic division, look for a 0 remainder. So it's just like the bonus question. We're setting the dumpster on fire. It's a problem we know how to solve. Synthetic division, 0 remainder. We do it over and over. So we set the dumpster on fire a bunch of times. It's awesome. So our theorem, our tool to do this is going to be I'm going to call it the rational 0 test. How do we pick these things? How do we generate this list of things to try? And the way we do that is called the rational 0 test. First, if we're talking about a rational number, what do we mean by a rational number? Let's make sure we understand that. It's a fraction of is 2.5 over 4.7 rational? Or do we know? Rational means it's a fraction of integers. We could think of them as whole numbers. So something like a over b, where each of these is an integer. So 3/5, 4/7, 1/2. Whole numbers are integers also. If our denominator is 1, 1, 2, 3, 4, 5, etc. So a rational number is a fraction made of integers. So what we're doing with the rational zero test is looking for solutions that are rational numbers. So I'm going to say for f of x, we have a polynomial, a sub n, x to the n, a sub n minus 1, x to the n minus 1, plus dot dot dot, a1 x plus a0. This is equal. And we're saying that a sub n and a sub 0 are not 0. The possible rational zeros of f are, I'm going to call this a sub 0 p, and I'm going to call a sub n q. I don't know why mathematicians chose p and q for these. That's just traditionally how we label them. The possible rational zeros are plus or minus the factors of p over plus or minus the factors of q. So this list that we get for the factors of p over the factors of q are going to give us numbers to try to do synthetic division with, to find our zeros. Now it could turn out that our functions don't have rational zeros, so this test wouldn't give us those roots, but for the most part, not for the most part, for what we're going to do, our functions are going to be nice, and when we use a rational zero test, we'll be able to get some rational zeros out of it. So this is going to give us our list to test. This plus or minus factors of p over plus or minus factors of q. We'll do our synthetic division. We're looking for zero remainders. So let's look at an example. This is pretty easy to apply. We know how to do the synthetic division. We just need to generate this list. All right, so questions so far. So let's say we want to solve, similar to our first question. What was that? We want to solve x to the third minus 7x minus 6. All right, so this is my p, and this is my q. So I'm just going to make a list. The factors, plus or minus the factors of p. What are the factors of 6? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Factors of q. This is nice when this happens. What are the factors of q? Plus or minus 1. So for this function, our possible rational roots are just plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. We like when q is 1 because our denominator, q is our denominator, the p over q. Our denominator is 1. If q happened to be 2, then we would have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. We would also have, if we had a 2 here, plus or minus 1/2, plus or minus 2 halves, which is just 1, plus or minus 3 halves, and plus or minus 6 halves. So we'd have to have all those denominators as well. So it's nice when we don't have to worry about those denominators. Yes?
So do those ever simplify, like 6 over 2?
Yeah, that would be just 3.
And then you can just keep it like
Just
the other
3,
3
yeah,
for P.
exactly. All right, so let's keep going here. Plus or minus 1 is very easy to test in your function. It's nice to see if that's a 0 of your function. So let's test plus or minus 1. F of 1, it's just 1 minus 7 minus 6. Is that 0? 1 minus 7 minus 6? No. I'm just going to say not equal to 0. All we care about is whether or not it's 0. F of negative 1 is, to find f of negative 1, just change the signs on the odd powered exponents. So that's going to be negative 1 plus 7 minus 6. Is that 0?
Yes.
Yes. Now, after plus or minus 1, if you didn't get a 0 with plus or minus 1, I would then start doing synthetic division, because then it gets harder to plug in the number. But plus or minus 1 is easy to test. So we know that negative 1 is a 0. So we're going to do synthetic division with negative 1. Yes?
Shouldn't the negative 6 and the f of negative 1 be a plus 6?
No, so since there's no variable, it doesn't change. That constant always stays whatever sign it is. So we're only changing the signs on the odd powered exponents. All right, so we know if we do synthetic division by negative 1, we should get a 0 remainder, and then we'd have a quadratic function. So let's set this up. I need a 0x squared minus 7 minus 6. So we get a negative 1, 1, negative 6, 6, 0. So there's our 0 remainder. So we have x cubed minus 7x minus 6 equals x plus 1 from this. This is x equals negative 1 times x squared minus x minus 6. And does this factor? Yes? So we get an x, what is it, a 2 and a 3, and it's got to be a minus and a plus for my factoring. So there's our fully factored form if the question asks us to factor. So our zeros, or our solutions, are x equals negative 1, x equals negative 2, and x equals 3. Would be the solutions to that equation. Yes?
Isn't there a way to plug it into the quadratic formula too?
From here?
Yeah.
Yeah, you could plug that in the quadratic
And
formula.
it would give you those.
It would give you those, yes. If you can factor, I prefer to factor than use a quadratic formula.
Okay.
Quadratic formula is like a hammer. It'll always work. You can always pound the nail in with the hammer. But if we can finesse it in by talking nicely to it, then that makes it, I think it's nicer that way. But the quadratic formula will always work on a quadratic function. But when you do the quadratic formula and you get integers out, that tells you, oh, I could have factored that. All right, questions there? Let's look at a higher powered polynomial, a 4th degree polynomial, because here we did one round of synthetic division, and then we could use the quadratic formula or factor. Let's look at one where we have to take one more step. So let's find the real zeros of x to the 4th minus 3x to the 3rd plus x minus 3. So there's our function. 4th degree polynomial. Solving this using other methods, very difficult. It turns out there are ways to solve a cubic polynomial and a fourth degree polynomial and a fifth degree polynomial by doing something like the quadratic formula. For a third degree polynomial, it gets way more complicated. And for the higher ones, it's way, way, way more complicated. So we prefer not to have to do it. But it's impossible to do it any other way for anything above a fifth degree polynomial. Yes?
Is Q always the leading coefficient?
Yes, always. All right, so this one, we're going to find our possible zeros. Whoops, that's P. And Q. It's always nice when Q, our leading coefficient, is 1, because we don't have any fractions to deal with. So our possible rational zeros are just the factors of 3, plus or minus 1, and plus or minus 3. Because Q is just 1, so our denominators are 1. All right, let's try out f of 1 and f of negative 1. See if those are zeros. F of 1 is 1 minus 3 plus 1 minus 3. Let me make sure I wrote that. Is that 0? Not equal to 0. That's all we care about. Is it equal to 0? F of minus 1 is change the powers on the odd, or change the signs on the odd powers. So it's going to be 1 plus 3 minus 1 minus 3. Is that 0? Yeah. Yes. So now we're going to do our synthetic division. This is similar to the last one. It's nice when plus or minus 1 is a 0. If plus or minus 1 isn't a 0, then we go on to plus or minus 3. I do synthetic division after that to test it. All right, so we know if we do synthetic division by negative 1, we should get a 0 remainder. So I get a 1 minus 3, a placeholder for the x squared, 1 minus 3. And we'll do our synthetic division. All right, so there is our synthetic division after the first round. So I'm going to write over here that what we have is this. We have x plus 1 times x to the third minus 4x squared plus 4x minus 3. Now, we could start over and do our p's and q's here and synthetic division. But if we have possible factors of this thing, isn't that also still the possible factors of this whole thing? Yeah. So I already have the ones I can test. So I'm just going to do synthetic division again with one of these other possible ones. Because if it's a factor of this whole thing, it's got to be a factor of these multiplied together. So we can try it and see if it works. So which one should we test next out of our list?
3.
Let's try 3. We could try negative 3. We've got to try something. So I'm going to do synthetic division again and see if I get a 0 remainder. So we get a 3 minus 1, negative 3, 1, 3. There we go. Yes?
Why can't you just say f of 3 and plug it in?
You could. Usually it's easier to do the synthetic division than calculating it. And if your number is a little bigger, if you have to, like, you'd have to do 4 to the 4th minus 3 times 4 to the 3rd. So you'd have to do those calculations. But with synthetic division,
Okay.
you just multiply and add.
Okay.
All right, so we found the other one. So 3 is a 0. If we tried 3 and it didn't work, we'd have to go back up here and try negative 3 to see if that's a 0. We got lucky and found 3 is a 0. If we tried 2 of those, if our lists were longer, we tried plus 3 and minus 3, those didn't work, we'd have to try whatever is next on our list. And keep going until we find another 0 remainder. Most of the problems that we do, usually the numbers are small and you don't have to go through a big list. I took one of the graduate courses that I took. We had to do factoring, and we learned a lot of different other techniques for factoring. And we had to do synthetic division with large polynomials. And I remember doing pages of synthetic division with factors that didn't work. It was a lot of work. But we won't have to do that. All right, so now we know that we have x plus 1 times x minus 3, the 3 from here, times whatever we're left with here, x squared minus x plus 1. And I'm going to, we would try, does this x squared minus x plus 1 factor? No, we can't factor that. We could try the quadratic formula. So I would say x equals 1 plus or minus the square root of 1 minus 4 times 1 times 1 all over 2. Well, look what happens here. 1 minus 4, negative 3. Square root of negative 3 is going to be complex. So this gives us a complex solution. And this tells us find the real zeros. So we don't have to worry about this. We'll do this next time. Talk about the complex solutions. So this is as far as we can factor this. So our real zeros are x equals negative 1 and x equals 3. The other two are complex. And this would be our factorization. And we'd be set. If it were a 5th degree polynomial, we'd get down to here. This would be a 3rd degree polynomial. We need to do one more round of synthetic division to reduce it, to reduce our polynomial to a quadratic. Our goal is always to do enough synthetic division that we're left with a quadratic that we can either factor or use a quadratic formula. All right, questions there? So chapter 2 is just a lot of synthetic division over and over. Yes. All right, so the next thing we're going to talk about is another way that we can reduce the number of choices that we have to try synthetic division with. And this is called Descartes' rule of signs. Descartes was a mathematician and philosopher. All right, so Descartes' rule of signs. We have a polynomial, a sub n, x to the n. This polynomial we've written a bunch of times. Plus dot dot dot, plus a1x, plus a0. And for Descartes' rule of signs, we're saying that a0 is not 0. So we have a constant out here at the end. Descartes' rule of signs, you have to have a constant. Descartes' rule of signs says it has two parts. The number, that's just how many, of positive real zeros of f is the number of sign changes in f or less by a multiple of 2. And we'll talk about sign changes in just a second. It's really easy to figure out how many sign changes we have. 2, the number of negative real zeros. of f is the number of sign changes in f of negative x or less by a multiple of 2. All right, so let's take a look at what Descartes' rule of signs is telling us. So let's look at a polynomial. Let's say we have f of x is 3x cubed minus 2x squared plus 5x minus 1. The number of sign changes means how many times does the sign on the coefficient go from positive to negative or negative to positive. So here we have positive to negative. There's one sign change. Here we have negative to positive. There's one sign change. And here we have positive to negative. There's one sign change. So we have 3 sign changes. So Descartes' rule of signs says we have 3, or I have to go down by a multiple of 2, 3 minus 2, 3 or 1 positive real zeros. F of negative x. F of negative x is very easy to figure out. Change the sign on the odd powered exponents. F of negative x is just going to be negative 3 x to the third. This is an even exponent, so that doesn't change because negative times the negative stays positive. This is odd. 1 is odd. How many sign changes do we have there? 0 sign changes. So this tells us we have no negative real zeros. So when we make our list of plus or minus p's over plus or minus q's, we're going to throw out all the negative ones. We don't have to test any negative ones because none of the zeros are negative. Descartes' rule of signs says none of them are negative. So that's cut down the number of choices we have by half. So that's how we would use Descartes' rule of signs. So Descartes, the xy plane, another name for the xy plane is the Cartesian plane, or Cartesian coordinates, named after Descartes. Do you know why horses are bad at graphing? You're putting Descartes before the horse. All right. Let's look at one more, just to make sure we see this, how the sign changes work. F of x equals 2x to the third minus x squared plus x plus 4. So let's count the sign changes. We have 1 there. Oops, I've got to just ran out of power here. Give me just a second. There we go. All right. So we have 1 there, and we have 1 there. So we have 2 sign changes. So that tells us we have 2 or 0 positive real roots. And f of negative x, change the sign on the negative powers. Negative 2x to the third minus x squared minus x plus 4. So we have just one sign change there. So that tells us we have one negative real 0. So if I did Descartes' rule of signs here, I would try the negative, try negative 1 first. Once you found one negative real 0, then you're done. You don't have to try any more negative numbers. So that's how Descartes' rule of signs can help us limit our choices. Now, if you came up with a polynomial that had 5 sign changes, that would tell you you'd have 5, 3, or 1 real 0, depending on which sign change you had. If you had 6 sign changes, you'd have 6, 4, 2, or 0. Okay, you go down by 2 until you get as small as you can. All right, questions? So Descartes walks into a bar. The bartender says, "Would you like a drink?" And Descartes says, "I think not," and disappears. Descartes said, "I think, therefore I am." I think not, therefore he was not. All right. All right, so I have one question for you. What if we wanted to find the zeros, something x to the 4th plus 3x squared plus x? So our rational 0 test, Descartes' rule of signs, says that we need a constant out here to apply those things. What are we going to do here? What is it? Factor. What do we have in common here? There's a common x in each term. Factor out that x. And now we know one of the zeros is 0 from this. And then this should be an x. Sorry. Thank you. So then we would do our p's and q's and Descartes' rule of signs here. On this polynomial. And someone just pointed out there are no sign changes here, so there are no positive real zeros in this thing. So they'd have to be negative. And what are our choices here? Plus or minus 1. Is 1 a real 0? If we plug in 1, do we get 0? Oh, it'd have to be negative 1. Does negative 1 give us a 0? Negative 1 minus 3 plus 1? No. So that tells us our zeros aren't rational. So this one would be kind of tricky. All right, so if you see something like this, don't worry that there's not a common or not a constant term there. That probably means you can factor to begin with and then do something. Okay.